Excellent. You're here. I've brought you here to teach you about calorimetry and measuring heat in our fifth lecture on physical behavior and matter. Shout out to Milksy. There you go. Let's hit up our learning targets. We're going to see how to track changes in energy and phase changes using physical constants for water and heat equations. So we're going to take what we learned last lesson in heating and cooling curves, and we're going to take it to the next step and actually quantify, put numbers on the amount of changes in heat that are occurring during phase changes that we would track in a heating and cooling curve. To cover that basics, calorimetry is what we call this. It's the measurement of heat stored in a substance. A calorimeter helps us measure it. And here's a picture of a high-class calorimeter. It's an illustration, actually. So what we have here is a sealed bomb at the bottom, right down here, that we would put a chemical reaction in. When that reaction happens, the heat that it releases or absorbs moves out of the bomb into water. That water, since heat causes the atoms to move faster or slower, that water changes its temperature, and the thermometer we have here would tell us how much the temperature of the water changed by. And as a result, we'll be able to do the calculations I'm going to show you and figure out how much heat is absorbed or released in a phase change or a temperature change for water specifically. Okay? So on table T, we've got some equations. There's what I like to call Q McCat, Q equals M times C times delta T. Then we use that when a temperature is changing. That's what delta T means, temperature changing. Delta is a change, triangle means change, and whatever variable comes after that means we're talking about a change in it. Okay. The next one is Q equals MHF. This is used when we have fusion, aka melting. So when temperature is not changing, position of particles is changing. We have to use a different equation because we have no delta T to work with. So we have a different equation to use during melting. And finally, a third equation, Q equals MHV, the same thing. We use this during vaporization, though, because temperature is not changing, but position of atoms is, and we have to tell how much energy is related in creating that energy of position, that change. Okay, so specific heat capacity. These are all variables found on reference table. I think it's reference table B right here on the reference tables. C is the specific heat capacity. Oopsies. It is 4.18 joules per gram degree Celsius. It's kind of showing up there. Table B, we've got HF and HV. Here the variables are right there. There's the numbers. All right. Sorry that animation's not showing up quite right. But what I want to point out is that it takes more heat to vaporize water than it does to melt water. Okay, for water to turn from a solid to a liquid doesn't take a ton of heat, but for water to turn from a liquid to a gas takes a ton of heat, which is why the HF and HV variables are different numbers. Okay, we're going to see a cooling curve and a heating curve, and this is we're going to label up where to use each equation. Okay, not the phases, but where to use each equation. The heat of vaporization equation is on the highest flat. The heat of fusion equation goes on the lower flat. And anytime we see a change in temperature, we will use the delta T, QMC delta T equation. So we'll use that in 3 different zones. Okay, so these are the places that you would use each equation if you were tracking heat changing of a substance using a heating or cooling curve. Guess what? Even though the curve's profile looks different, high to low, the same equations go in the same spots. Vaporization on the high flat, fusion on the low flat, and delta T on all the slants in between. Okay, so these are where you use each equation. But I need to show you how to use the equation and what kind of problems show up with this stuff. So here's an example heat flow calculations. How much heat is absorbed when 100 grams of water is heated from 20 Celsius to 75 Celsius? So we'd have to use QMC delta T in this case. So I always write out my equation first. Q equals M times C times delta T. And then I start substituting variables. So Q equals M. M is mass, 100 grams. C, that's a constant, always the same, 4.18 joules per gram degree. And then the change in temperature. Well, the change in temperature, it changed from 20 to 75. So the temperature changed by 55 degrees Celsius. So times 55 degrees. And when you do the math, the degrees drop out, the grams drop out, and the joules stay behind. So what you have is just some straight multiplication. 100 times 4.18 times 55, and you'll get your answer. So do that math on your calculator, okay? All right. So calculating change in temperature, given amount of heat lost or absorbed. So if we're given amount of heat, how much would the final temperature be? We're going to use the same equation, but we're going to play around a little bit different. Q equals M times C times delta T. But this time we're given Q, which is 1,000 joules. And we have 100 grams. We got 4.18 joules per gram degree again. And then we have our delta T. This is the variable that we're trying to solve for this time. So we're finding out how much the temperature of the water changed by. And when we solve for this problem, the grams and the joules drop out. Then we get delta T equals 1,000 divided by 100 times 4.18. And this is going to be equal to your change in temperature. So if we have the temperature that the sample started out with, 25 degrees, we're going to add that to our delta T to find our final temperature. If it started at 25 and we know how much the temperature changed by solving for delta T, we're going to have our final answer there. So your job is to solve not only for delta T, but solve for the final temperature as well. There are other equations. How much heat absorbed during a phase transition. So let's use the different equation and see how we go. How much heat is absorbed to melt 50 grams of ice at 0 degrees Celsius? Well, melting equals that I have to use Q times M times HF. And Q is going to equal the mass, 50 grams, times HF, which I'm reading off of my reference table, 334 joules per gram. Gram units drop, and we get Q equals 50 times 334 in joules. You solve it for your answer. The phase transition temperature calculations and heat calculations are much easier than the delta T ones because you don't have to figure out a change in temperature. You have to just decide which is the right equation to use. Let's do another one. We're going to heat released 60 grams of water when it's frozen. Well, it's frozen, so we're going to use the same equation, Q equals M times HF. And so Q equals 60 grams times 334 joules per gram again. So even though we're freezing and not melting, we are still left with the same mathematical process. This time you're going to do 60 grams times 334 joules per gram, and you'll find how much heat it took to release when that was frozen. We got to do some vaporizing, so let's check those ones out. We're just going to use a different equation with a different variable. Instead of QMHF, we're going to use Q equals M times HV, because V is for vaporization. So Q equals M times HV. And then we got to use a different number for HV as well. This time we got 19 grams, and HV, I'll read off table B, 2260 joules per gram. Grams drops out, leaving us with the units of joules only. And you solve the math, and you'll be able to tell me how much heat was absorbed in vaporizing this sample of liquid. And we're going to do the last one, which is a condensation. Okay, same equation, but instead of heat being absorbed, it's heat being released. Okay, so I'll use the same equation. I always write it over. Q equals mass, 70 grams. HV is 2260 joules per gram. Grams drops out, leaving the units of joules at the end, and U with a simple multiplication problem to solve. Okay, so heat flows in and out of objects. These equations I've showed you today just shows us which equation to use when we're talking about water and heat flowing in and out of water. Okay, and I believe that's the end of our lesson. So there's a lot of practice in the practice pack about this. Check it out. See y'all later.